Okay, hello again. We're working through the fixed point iteration method and trying to do it in a bit more detail than was done last year. So I just want to remind you the two sort of results that maybe you found last year that we want to really prove today. So first of all, remember with fixed point, the idea is to find the fixed point. The fixed point is where x, the line y equals x equals g of x. And when you have a graph like this with a nice shallow gradient of g of x, so g prime of x, the prime indicating the first derivative, the modulus of that is less than 1. Okay, so you could have a line going like this. And when you do this, you apply the fixed point iteration, x equals g of x, and it nicely cobwebs or spirals into the solution indicated by the arrow here. Okay, so that's all well and good. If you were to just take that same graph of g and increase its gradient so it's greater than 1, so g prime of x is greater than 1, then it diverges, it doesn't work. So you see it spirals outwards, x equals g of x. Okay, so that's the one we want to prove. Now, my understanding from John Thupman's note is he very briefly showed some Taylor expansion. I want to sort of prove it a bit more rigorously than last year about why this diverges when the gradient of g is greater than 1 rather than less than 1. Okay, so I'm just going to flick then over onto the board. Here we go, and we'll proceed. So let's just recall from last time. First thing is you had mean value theorem. So I'm just going to call it MVT because we've done it last time. So mean value theorem. And that is that the first derivative anywhere in your domain, so anywhere in your domain is indicated by this variable psi, is equal to the gradient of the chord constructed by the two endpoints. Okay, so we've got that, we're going to use that. And then we had a couple of definitions. We had definition 1, which was simply your fixed point algorithm, just written down. And then definition 2 is the true solution. That's x equals x star. And that's basically saying when you could reach the true solution, xn plus 1 goes to xn goes to x star. Yeah, they all converge together. So just like that case of it spiraling into the solution. So when you do that, then you have basically the x star equals g of x star. Okay, so those are the background we sort of set up last time. Now we're in a position to prove the convergence of the method. But let's just state the theorem before we get too far away. Okay, so I'll call it theorem 3, or more, you might want to call it fixed point theorem. Is basically the fixed point iteration converges if g prime psi modulus is less than 1, where this psi variable is anywhere in the domain. So we can say that is in the open interval from a to b, open because it's of a derivative. And of course, if that open interval brackets the root in the first place. Okay, so it's restating all the little bits and pieces in sort of a theorem form. Okay, so today, first main task for this video is to prove this and use our mean value theorem and our definitions to do so. And actually, it's not too, once you've set up those definitions, set up that mean value theorem, that you can quite quickly get to the solution, to the proof. The proof is not long. Okay, so let's do the proof. So first we define the error. Remember, this is a key thing with convergence, En. Error equals xn minus x star. Okay, so we define the error En equals xn minus x star. It's just the difference between the numerical solution, remember, and the true solution. And for convergence, we're expecting En to go to 0, or the modulus of En to go to 0. And this is a key principle that will go throughout this term's material, in particular, of convergence. The first thing we can use is we can use our definitions. So now we use definitions 1, 2. So we're going to state the first definition now. It was done in xn plus 1, but definition 1 we're going to actually let's just scroll back a bit. Okay, let's just use definition xn plus 1, and we're going to write, remember that was xn plus 1 equals g of x of n. Actually, we want it in terms of xn, so we're going to have x of n equals g of x of n minus 1. Okay, so that's just replaced n with n plus 1. That's going to allow us to substitute in for xn. And then, of course, definition 2 was simply that x star, your true solution, is g of x star. So that's very helpful because it allows us to express our original error into x variables, into differences then in terms of g variables. And then you can see where we're going to go. We're going to then use a mean value theorem. So we're going to subs in definition 1, definitions 1 and 2 here, written in our form, and then we just have our error then xn is equivalent to g of x n minus 1, right? Minus g of x star. Okay, so that's the first bit. He's just remanipulating these, manipulating our error variable in terms of g variables. Now what we have is a difference in g variables at 2 points. We have the value of the g at the root, if you like, and then the value of g at xn minus 1. And if you remember how mean value theorem is structured, it's relating the difference of function values across the domain to the gradient within it. So that's where we're going to enter the mean value theorem, and then this is where the gradient comes in. So that's the last bit of the theorem. Okay. So let me just write, I think just for continuity, I'm just going to rewrite that line up. We've got plenty of space. And then we use MVT, mean value theorem, in the form, again, we want to get it in the form we want. And that is basically saying that g prime, and now I'm going to give our psi variable at a time step, n minus 1, equals the difference, the gradient of the chord, which is g of x n minus 1 minus g of x star divided by x n minus 1 minus x star. Okay, so that's just our mean value theorem stated in the form we want. And of course here we've got the differences of g variables in a variable, so we just substitute in. So that implies that E of n now equals g prime psi of n minus 1 times x n minus 1 minus x star. Okay, so we're getting somewhere. We're getting somewhere which intuitively seems right. We want to prove that its convergence depends on g prime, but and we also want to have a rule for the error. Okay, so that equals g prime psi of n minus 1, and that's the last thing to observe then, is we have a difference at x n minus 1 minus x star. That is your error, but rather than at step n, it's at step n minus 1. So we have a nice recursion relationship between error at one step and error at a previous step. Now, stated as it is, let's actually put the error law down here. It's not quite as rigorous as we'd like, because we'd like to have that to be the modulus of the error. Remember the general convergence law that we set up one or two videos ago was in terms of the absolute value of error. But we can see what we're getting here is we're now getting the error is proportional to the single power e to the 1, if you like. So we're coming towards a linear convergence law, just like the bisection. But with the bisection, the coefficient was a constant. It was basically dependent on it halving each time. Now we have a coefficient that's dependent on g prime. Okay, so we're going to take the modulus and use the identity modulus of AB equals A modulus B modulus. Some would say that's obvious, but I bring it up because we're going to use other types of this when we get on to using vectors and norms. We're going to use an analogy of this. So I'm going to actually, this has got a name, believe it or not. It's called multiplicativity. Okay, just sort of store that bit of information for later when we get onto vectors, and we'll see that actually you have an equivalent of this relationship. But it's basically saying if you take the modulus of a product, it's just the product of the moduli, which is easy. So that implies then the modulus of error. So this is the more rigorous way of stating the convergence laws. It is g prime psi m minus 1 equals e n minus 1. So we have linear convergence. So it's like, in that sense, it's like bisection method. It's got a power of 1, but it's controlled by the coefficient g prime psi m minus 1. So if you look back at your notes, we set up a sort of the general convergence law. We have en is a e to the n to the q. Q is 1, the power that we're going to, but the coefficient a is just g prime. So it's a more subtle coefficient than bisection. So there's conditions for when it does work, conditions when it doesn't. Okay, so method converges, then when G prime psi n minus 1 modulus is less than 1, because you want the error to decrease with each step, and that's what the condition is. Okay. So we can just scroll back now and look at our different evolution rates. So now we have fixed point method gives you modulus v n equals G prime psi of n minus 1 modulus e n minus 1. So it's linear, but then bisection, we did it in terms of the maximum error, but you can still compare the two. We have the maximum of the error equals a half. I'm going to move the half right outside to be equivalent. Max. So we did it in terms of n plus 1 and n minus 1. En. Okay, so you could rewrite this in terms of n and n minus 1 to make this count. But the key thing is this coefficient, right? You've got a half. You've got a half here. Then you've got G prime there. Right. So if G prime psi of n minus 1 is less than a half, i.e. this coefficient, then fixed point converges faster than bisection. All right. So they're both linear convergence. So one is not going to be massively faster than the other, but one is going to be faster if it's G prime is less than a half. The other thing to say is that for the fixed point method, there's some problems that just lend themselves for being set up in this x equals g of x form, and thus that's another reason you'd use fixed point iteration. Okay. To find the solution you're looking for. Okay. So that's fixed point method proved, and we now have a rationale for why when we plot the different graphs it works and when it doesn't work. And I think that's a good place to pause, and I will see you in the next video. Okay, let me, I'll tell you what, let me just get face up. So that's me again. Okay, just me signing off again for another video. So we've done the proof of fixed point method today, using mean value theorem and the definitions of fixed point. And now you have a rigorous way forward with fixed point method. Okay, see you again. Bye for now.